Good morning, science adventurers, and welcome to Forschungszentrum Jülich. Science is all about predicting the future, and one thing that we might want to predict is motions of particles. For example, say we have a protein. To know its behavior in chemical reactions, biological systems and so on, we need to simulate the forces on every atom. In a large system like this, there are about n squared minus n particle pairs. Computing the force between every pair directly is computationally prohibitive. It has O of n squared time complexity. But we can do better. The fast multipole method is a quicker algorithm for solving the same problem. The way FMM operates is by grouping particles into clusters, such that within each cluster, particles are close to each other, but the clusters themselves are far. So if we have a group here and a group here, there would be two clusters. Within the cluster, we evaluate the forces directly using the naive Coulomb solver, which has O of n squared time complexity, but in this case, n is limited to the cluster size. Between the clusters, instead, we use a multipole and local expansion to encapsulate the effect of electrostatic interactions in a single computation instead of computing every pair directly. My project this summer was to see whether we could execute FMM in its entirety on a graphics processing unit. To understand how we could do that, we first need to know a bit about how GPUs work. GPU hardware generally falls within what's known as a single instruction multiple thread architecture. This is different from standard architectures used on things like CPUs because it is less general purpose and it is not meant to be. The price that we pay in having a more limited programming model, we gain in exponentially increased floating point operation performance. So, in short, GPUs can turn numbers really quickly. To achieve its grouping of particles into clusters, which I described earlier, FMM uses a spatial data structure known as an octree. An octree is kind of like a binary tree, except every node has 8 children. The majority of work in the fast multipole method involves traversing the octree first up and then down, and processing information stored within the nodes. What we want to do is parallelize the whole thing such that as most work as possible is executed at the same time. For example, if we have multiple nodes at the lower octree level, we can execute our code on every node of these at the same time. However, when we get to the top level, all the other computation needs to wait until this level is finished working. So we have a stalled pipeline and we lose parallel performance. The way we deal with this issue on a CPU is by using what's known as a task queue. A task queue is a data structure which contains bits of work to be done. So you could think of it as having tasks. And each task could be something like compute the multiple translation between this position in space and another, or maybe compute the expansion given particle positions and charges, etc. So say we have 4 cores on a CPU. What the algorithm would do is for each core, the core looks at the global queue, then grabs the task from the queue, then executes it, and then grabs another one. So as long as the queue is constantly kept filled, no core will ever wait on anything because there is always some work to be done. And in particular, the way we alleviate the root of the tree problem is by backfilling the queue with other tasks which compute other elements of the algorithm which are independent of the root node. However, implementing a global task queue on a GPU presents more of a challenge than on a CPU because the programming model discourages global synchronization. So it discourages sending information between different cores. In particular, what we need is device-wide synchronization. So every core on the device has to communicate with every other core, which in general, historically at least, has not been available on GPUs.
The bulk of my project was to research whether it is possible, and if so, then how, to implement FMM on graphics accelerators in a way that best utilizes the available memory resources and processing power.
In short, the answer is that yes, it is possible on certain hardware architectures, and it is possible to optimize. However, the naive implementation is much worse than that running on a CPU, because the overhead due to having to synchronize certain elements of the hardware is much greater than on a CPU, which is built to do such things.